is my first time in the Islamic College University to be here. I normally speak very fast, and my request to all of you will be that please do interrupt and do stop me when you think that I am too fast for you people to understand. So those at the back, the moment you think that I am not audible, please just raise your hand. Okay? I am also very impressed. Normally in physics we do not expect so many girls. There is a Pashto verse which is my favorite. The Zalmona Pura Nashwa Grana Watana Jinekai Badigatina. So I am really impressed. This is very abnormal for physics to have so many girl students sitting here. And I thank you all for being with me this morning. It's not even morning, it's noon now. First of all, I would like to congratulate the University of Peshawar on its 75th anniversary. They have been serving the masses, and some departments were excellent. Some were working really hard to achieve the excellence. And perhaps many of you know that Peshawar University is the child of Islamic College. So it's very reverse thing. Normally you give birth to colleges, and here a college gave birth to a university, and then the college by itself became a university. So thank you madam for the invitation. Thank you sir for accepting our proposal to talk to your students. The talk will be about the Nobel Prize, but before drill into that, we will be having a few slides on the basics of quantum mechanics. So my request to you all will be that you might need to de-learn whatever you have learned so far and then try to learn. Of course, my sole purpose over here is that because I'm confused, so my purpose is to make you confused. So by the end of the lecture, if you are not confused, then my objective is not really achieved. So I hope by the end of this lecture, all of you will be confused what is quantum mechanics. This year is also International Year for Science and Technology and Quantum Mechanics is achieved. This is what we are celebrating because in 1925, the first time scientists came up with the idea that the classical picture is not enough to understand, and so they start making use of the quantum nature. This is where it started in 1925. So we are celebrating it now. The Islamia College, as I said, there were people who were working very hard, and this is what I always urge my students, that in science normally is very little role of the prodigy. There is very little role of somebody being intellectual. What pays off in the end is the hard work. Many of the PhD doctors that you see is not that because they were really clever. It's not that they are really very smart. It's just because they know how to work very hard. But working hard with a little bit of smartness always pays off. So if you are in physics, it's not only you work hard, you have to be a little smart as well. So this is a little difference between physics and the other subjects. In other subjects, it might be that you just do hard work, but in physics, you do need to use your brain a little, okay? Just a little. So, okay, thank you. I love you guys, thank you. Now let's come to the menu. You see, this is always I share with my colleagues that in Pakistan and Pakhtun culture we have this tapa. Before the tapa we have the Qurban. So when you go to these music functions and they will say the Qurban is very long. Very long, they stretch it, Qurban, and then they stretch it so much. At the end they just a very small tapa. So this was all Qurban so far, okay? So, right. So the main way is that we'll have some basics of quantum mechanics. most of you guys perhaps have gone through, especially those who are in the senior classes. How many of you have gone through a course on quantum mechanics? Not many. There are quite a few. Okay, I'm happy that you are not gone through, because you will be confused for a longer time. Okay. And then the next one will be the Nobel Prize, because we would like to understand what is the Nobel Prize about. Okay. And then of course the third one. So it's a very brief menu. So three things only. First is the quantum mechanics basics, and then the Nobel Prize, why the Nobel Prize was awarded for that, and then we'll have some questions. Okay. Now let's go to the basics. Okay. In between, just to relax it, I have these things for you as well. Okay. So if you choose to stay in physics, this is the beauty of physics. If you choose to stay in physics, you have to be in physics with full conviction. It's not they say, look, I'm in physics, I'm not sure, maybe after the time I'll go to another field, I'll do that and do that. So if you want to stay in physics, do so with full conviction. Full conviction means nothing else doing. Full concentration on physics. And then you should be able to shunt orthodoxy. Whatever you hear outside, whatever you have learned before, you should be able to just oppose it. If people in the street say something which is against the physics, whatever you have understood, not just learned, whatever you have understood, just say no, this is not according to the physics. Okay? You should be able to say no, this is not true. And then the next thing is, you should be able to challenge common perception. If somebody says nobody can go to the moon, you should be able to say no, it is possible. If somebody says nobody can go to Mars, you should be able to say no, it's possible. There are many videos on the social net saying nobody has gone to moon. If it is gone to the moon, then this should be done. You should be able to oppose it according to the laws of physics. Okay? Now, thank you. We have many of these topics which are very common to those who have just seen quantum mechanics. If you see these topics, we have, for example, photoelectric effect, wave particle duality. These are the things we are going to just briefly go through, just a revision for all of you. Now before that, let's talk about something. The quantum mechanics students normally, they hate this thing. Whenever you say quantum state, you show them this psi notation is so worrying. Why psi there? Those of you who have gone through quantum mechanics, and then the psi is then put inside a Kit-Bragg notation. God, this is so horrible, Kit-Bragg notation. But what we are going to do is not going through the detailed mathematics, just to tell you what is a quantum state. It's just a mathematical tool, but this tool is so beautiful. It gives you everything about a system that could be only described by the laws of quantum mechanics. So it's just something so beautiful, this state. So this state has some key characteristic. It has the description of the system, and then you can have the value of those properties at any other time. But you will have to use the Schrodinger equation. Don't worry about the Schrodinger equation. So at the moment, Schrodinger equation just like the Newton's second law, but for now just forget it. Okay? So what you can do is you can apply this law to find out the condition or the state of a quantum system at later time, provided you know it earlier. At time t equal to 0, if you know it, and if you know the Hamiltonian, those of you who have heard the name Hamiltonian, in classical Hamiltonian is just the total energy. So this is a classical thing, okay? But Hamiltonian quantum mechanics will be an operator, but we don't go into that detail, okay? Now, it allows to predict the probability. So remember, those of you who have seen the quantum mechanics book saying psi is a function by itself is an amplitude, but if you take the square of that one, you get the probability of that property. Okay? So these are the properties. So upon measurement, this is the beautiful thing about the quantum mechanics. This is something nice. So if you measure something, then that function collapses. You look at the function, this quantum state for position, and then you say, okay, I'm going to measure it. So the moment you measure it, then the function is collapsed. Okay? So it's no more quantum mechanical. This is the only thing which is making it so difficult to use the quantum mechanical concept at macro scale. And this is how the Nobel Prize was awarded. Okay, the quantum state could be pure, it could be just one. For example, you are looking at the polarization of light, you have horizontally polarized light. So this is just one. If you look at spin, for example, spin up, this is just a pure state. But if you have spin up and spin down, that will be a mixed state. So for pure state, you have vector. Okay, when it is a mixed state, you have the density. Okay, so this is the only thing, but you don't have to. This is just the nomenclature that we'll be using later on. So I thought perhaps it'd be good that you know it. Okay, these are the quantum objects normally we see. So do not constrain it. This is only one thing that I want to share with you. Do not constrain it only to particles. And also, I don't call quantum object is particle. This is the only thing I'm requesting you to learn. So from today onward, we'll be talking about quantum objects, not particles. Okay, quantum objects, not particles. Okay, because you can see the example, we have the elementary particles. Elementary particles being, for example, electrons, photons and quarks. Okay, protons are not elementary particle. Okay, right. So you have composite particles and you have molecules. Some of the molecules, carbon-60 molecule, could be a quantum object. And also you have artificial quantum object, quantum dots. They are quantum particles, quantum objects. Okay. So the particle is not the only definition for quantum objects. Okay. There are certain properties. If the object or the system obeys those properties, those laws, the quantum mechanical laws, then we call it quantum objects. Okay. Now, an object, it could be atom, it could be particle, not just particle, could be atom, could be particle, could be molecule, it could be a combination of different systems that will be making a quantum object. And this one more thing, perhaps many of you have learned that quantum object is a particle which is sometime having a property of a particle and sometime has a property of a wave. Okay, de-learn it. Okay, it's not like this. Okay, quantum object is an entity by itself. It's neither a particle nor a wave. Okay, let me repeat. Quantum object is an entity by itself which is neither a particle nor a wave, but it so happens it shares sometime its property with wave and sometime properties with particle. So it's an entity by itself. Okay, so it's not a particle, it's not a wave, but it so happens sometime it shares its property with wave and sometime it shares property with particles. Okay, this is good, you have learned this now. By the way, I'm not really fond of the strings. There is string theory, perhaps those of you at this advanced level, but string is also treated or considered as a quantum object. Okay. Okay. Usually it's favored. Usually, I'm using the word. See, you have to be careful with the word that I use. Usually, it is favored by small mass, small size. Okay, low temperature. Okay, these are the usual thing for quantum objects. Okay, and as I said, the small size, I put it in parentheses, and also there is a sign of interrogation as well. This is what was challenged in the Nobel Prize that we're going to talk about. Okay, it's not just a small size. Okay, the transition from quantum to classical is not about sizes per se. See, the 2025 Nobel Prize is about this thing. So you don't have to, from now onward, don't say it's a small size. Quantum object is not just a small size. Okay, what we do is normally you zoom in. Let's say you have sodium chloride. If you zoom in into sodium chloride, then you will have the sodium ion and chlorine ion. This is a very standard metric level chemistry or physics that you have. So you have sodium ion and you have chlorine ion. And you can see the size of the sodium and chlorine ion total together is 564 picometer. And a pico is 10 power minus 12, 10 power minus 12 meter. So this is such a small thing. So we zoomed in. But sodium chloride by itself may not, I'm saying, use the word, may not be a quantum object. Okay? So what you do, you zoom in further. Now you have this picture. This picture is also wrong, by the way. Okay? In physics, we do not accept this picture where you have the nucleon and you have the electrons revolving around. This is wrong. Okay? It's not like this. This is not correct, but it's very good for making the students believe in something. Even that is wrong when you think about the electrons having a cloud around a nucleus. That is also wrong. The electrons are normally in orbital, different states, energy states. Okay. So if you zoom in further inside the nucleus, the electron by itself, we don't know the exact size of the electron. We normally say it is less than 10 power minus 18 meter. Okay. We normally, if you remember, we say it's point-like particle. If it is a point, of course, there is no dimension. This is what we mean by point. But it has got some dimension as well. But right now we are saying is 10 power minus 18, less than, not equal, less than 10 power minus 18 meter. So if you zoom in further inside the nucleus, you have these quarks. So inside a proton you have quarks, inside neutron you have quarks. Okay, the valence quarks inside proton will be 3. Otherwise there is a sea of quarks inside, not 3. Okay, you have to relearn. If you have heard that inside a proton we have 3 quarks, 2 up and 1 down, then that's wrong. And also remember, the total mass of these 3 quarks is very, very small compared to the total mass of a proton. Proton is huge compared to the 3 quarks. So inside the proton you have many, many other quarks, and those quarks interact through gluon. And the maximum mass of a proton comes from gluon. Okay, and gluon is energy. So the total mass in the universe is not because of the electron and protons or neutrons, it's because of the energy. So we are all made of energy. Okay, the maximum we have is energy. Inside every proton, even 10 times more mass and energy than the actual the valence quarks that we have. Okay, but the talk is not about quarks and proton. Okay, this is just to okay. Now the electrons, the photons, and also the quarks, you don't have the exact position for them. So they will have this wave structure, many, many waves. So if you want to find out the exact position, you don't know the exact wavelength of it. Okay. So this is something I'm going to share with you. This is normally we alhamdulillah being having a belief in the revelation of Quran. Allah subhanahu wa ta'ala has made this universe stable on a very fine balanced number. If there is a little change in the mass of an electron, a little change, you know that by itself is a very small thing. The electron has a mass of 10 power minus 31, 0 and then 0.000030, 0 then 9, and that will give you the mass of an electron. And the size is 10 power minus 18. Similarly with proton, the mass is 10 power minus 28. So small numbers, so small position radii, but if there is a little bit of imbalance, little bit of change, this whole universe will be shattered. There will be no more universe. All these numbers, for example, Planck constant is 10 power minus 34. 10 power minus 34 joule per second, such a small number. But if there is a little change, this whole universe will be shattered. Okay? And then I want to share with you, let me see if I could play it. Okay, sorry, there was a small video I thought I would share with you, but it seems like it's not helping me, the system. Okay, this is another, you see, an old man advising the young lot. I hope you don't mind. I have these slides in between. Okay, the thing is, I have a belief that some of you one day can earn a Nobel Prize. Okay, this is my belief. I am telling you the truth. That is possible. I'm saying is whatever whenever you are here, you just learn. Oh, so nice. I was looking for it. Thank you. And then once you learn it, then you get skilled as well. And then try to innovate. And then you try to invent. And then try to bridge the gaps between whatever you have learned or whatever people know and the experimental proof for it, just like what these guys have done it. By the way, this experiment you will see was done in 84, but they got Nobel Prize for it now. Okay, and we'll share with you why is it. Okay, there was still Ya Qurban going on. Okay, so we are going to start with it now. Okay, I'm sure you know about this, right? And I'm sure also you know the picture as well. It's a very known picture. Einstein, right? Einstein got a Nobel Prize not for relativity, he got it for photoelectric effect. Okay? So the idea before Einstein was that light is a wave, okay, and it has energy h nu, where nu is the frequency, and frequency is inversely related to the wavelength, and wavelength could be in terms of color as well. So different color will have different wavelength, will have different frequency, so different energy. But the energy will be in terms of the Planck constant and the frequency h nu. Okay, nu is the frequency, h is Planck constant. Okay, and he said that if you shine, he did actually experiment as well on this one. If you shine light or certain frequency on a piece of metal, not necessarily metal, but let's say a piece of metal, then you will be able to eject some electron, provided the energy of the incident photon is either greater or equal to the binding energy of the electrons. Okay, so if you have this light which is infrared or red, and you shine it on potassium is a binding energy of 2.0, so you shine at this one, then you don't get anything. But if you have green, the green will give you energy, energetic electron coming out. The energy of the electrons are coming from the difference in the energy, the binding energy, and the energy of the incident photon. If you have blue photon coming in, you will get again electron, the energy will be higher because the energy of the blue is higher. Okay, there's one thing many of the students perhaps is difficult for them to remember, because whenever I'm in selection boards, I ask something basic like this: the electrons that are ejected, in this case they are bound electron. Okay, write it down with yourself, they are bound electrons. So in photoelectric effect, the electron ejection is those electrons which are bound to the system, bound electron. So all the energy of the incoming photon is completely absorbed by the bound electrons. Okay, let me repeat it again. All the energy of the incident photon is completely absorbed by the bound electrons. Okay, and then what happens? The bound electrons will leave the system. When it leaves the system, then there will be another electron coming down to fill that gap. Okay, now that gap, when it's filled by that electron, will have the radiations emitted as well. So there are two things: the outgoing electron is not the same electron. Okay, the outgoing electron is completely different, the outgoing photon is completely different, not the same photon. So that's why the wavelength of the outgoing photon will be different from the wavelength of the incoming photon. Okay, now perhaps you know that if the electron was not bound, there will be another kind of effect, and that effect is, those of you who are in the senior classes, if the electron is not bound, there is another effect, we call it Compton. Beautiful. We will have Compton effect. When you have free electron, then the photon will come in, interact with that, so you will have scattering, and then the scattering will result into Compton scattering. The photon will take another path and the electron will take another path. But here is the bound electron. Okay, so the photoelectric effect is clear. And also, please, if somebody asks you in the interview to define photoelectric effect, don't come up with this, the experiment which is normally in the book, where you have a tube and one side you have a node, and another side you have a cathode. You just start doing this. Cathode is hit with the photons, and then photoelectrons are emitted. Not like this. Okay, so this is enough for this one. Okay, the wave particle duality. This is very beautiful thing. De Broglie was a French scientist. De Broglie said that any particle, not just quantum object, any particle can have momentum associated with it. If it has momentum associated with it, then it can have wavelength associated with it through this relation. So of course, if you look at the relation that he came up with, the smaller the momentum, because you can see P is in the denominator, greater will be the wavelength. So there is always a limitation how small momentum could be and how great momentum could be. P is very high, then wavelength will be very small, small wavelength or a short wavelength is very, very difficult to measure. There is a technical limitation as well. Maybe you can go up to, let's say, a picometer. So picometer you can perhaps measure, but less than picometer you might not be able to measure with any spectrometer. So similarly, if the wavelength is kilometers, billion kilometers, there is no instrument that you can measure it with. Okay, so you have these values. If you put this n, you will get the wavelength for any particle. Okay, so you associate this one. Remember, you can rewrite this equation. P is h into h over lambda, and 1 over lambda, remember, is a wave vector. 1 over lambda is a wave vector. So P is equal to h into k. So what you can do is, you can go to this experiment. I'm not sure, maybe you have done it in your MEC classes, this experiment, some of you. There is a German experiment. I'm not sure you have it here. You have it here in the lab? Okay, you have it here. This experiment is telling you that you have incident electrons. They are coming and they are incident on crystal, and then you have diffraction. And after diffraction, you have a detector at different angle. You can just move around the detector at different angle, and you can work out the peaks. And those peaks will then give you the wavelength. You can work out the wavelength from there. So you use actually a particle, electron being particle, you used it, and you worked out the wavelength from it, okay, for using those equations. But at the same time, you have the Bragg's law. Remember Bragg's law? 2d sine theta is equal to n lambda. You have this relation, and if you put the value of theta and 2d is coming from the crystal, you get again lambda. Now when you work out this lambda is the same. You have 0.167. 0.167 coming from the particle nature, and 0.167 worked out from the wavelength nature. The two are equal. When the two are equal, that would mean then the particle can have, can be believed as a particle as well as a wave. Okay. I have 2 or 3 slides on this one, Heisenberg uncertainty principle. The reason I would like to emphasize more on this one, that some people think that perhaps is a technical limitation that we cannot measure the space and position simultaneously. Okay, I'll show you it's not the case. Okay, think about just this ball, a tennis ball somewhere in space. Okay, if you take a picture of a tennis ball, then somebody asks you to give me the position and the momentum or the velocity of this tennis ball. Okay, so for position you can say, okay, there's no big deal. You can just put the coordinates with it simply. This is what we in physics we do directly. You put the coordinates x, y, z, and then from x, y, z you can work out the position vector of the center of the ball. Then you say, aha, here is the ball. So I can tell you the position. So it's not a big deal. But now the thing is, once you know the position, can you tell from this picture the velocity or the momentum? No, because it could be in any direction. Right now this was just a picture. So the direction could be any. People, we have cameras which have a very long shutter time. So I can just open the shutter for a long time. So if you have exposure for a longer period of time, then you can have a ball picture like this. You have a streak of the ball. Now that you have a streak, that would mean it gives you the direction and the motion as well. Starting from one position to another position, and you can see here, from here to here, you know the distance traversed in this particular time, and then you know the direction as well. So now you know that, okay, I know the speed. Knowing the speed and knowing the direction means you know the momentum, because you know the ball mass. So you know, now you know the momentum. But what happened? Now you don't know the exact position. Estimate it out. And you say, no, you are from old age. We have cameras now, very, very fast camera. You go to a fast camera, it could be like this. Even faster camera you can have another one like this. So you know the direction as well as the actual value of the speed, and at the same time you know the position as well. But this is a ball. This is not a quantum object, and we are talking about a quantum object. Quantum object has a very small mass and has a very high speed as well. Okay. So now you know the location of velocity, but somebody would say, is this a technological limitation? A big no. No, it's not a technological limitation. There is an idea that some people think this could be, because if you want to, for example, work out the position of something, let's say use light to see the position. Light is photon. The moment photon interacts with this quantum object, it will just transfer some of its momentum to that quantum object. That would mean that object will no longer be having the actual momentum. So the momentum is changed. But that's not the actual idea. This is the cause, but this is not the actual reason for it, okay? So this is the cause, not the reason. The reason is that quantum objects share property with waves as well. So when you try to squeeze the wave, it's a very slimy, I'm not sure if some of you have played with slime, or my grains, they play with slime. So the moment you put in your hand like this, it just goes away. So just like very slimy wave, when you try to push it to one position, it goes away. So because of the wave nature, you try to work out the position, the wave will go away. It will not be there. But if you look now back into the quantum state, the mathematical tool that we said, psi, is so important. Psi is telling you that those of you who are used to this word commutator, I'm not sure if somebody would remember commutator, canonical commutator. So if you have, for example, a function which you put into a bracket, then it's a and b will be equal to ab minus ba. If a and ab is equal to 0, that would mean the two will commute. But in this case, they do not commute as a canonical one. In p and q, p is for momentum, q is for position. Those operators you put in a bracket will be ih. So now you see this so-called mathematics, which is not mathematics, it's a physics, is very powerful. Whatever we are doing it with these experiments is just one little symbol psi is giving us. So the state vector is defining the whole thing for us. Okay. Okay. So this sets a limit on the position, and that limit is in terms of the Planck constant. The Planck constant here we are using the reduced Planck constant, h bar or h cut is a reduced Planck constant. Okay. The origin is intrinsic. Is just like we are born with certain habits, those are intrinsic to us. Okay. Just like a particle electron has a mass, this is intrinsic. Just like a particle have a spin, which is intrinsic, so similarly this nature is also intrinsic. Okay. So that would mean that you can never measure the two simultaneously. Position and momentum, energy and time, you cannot measure them simultaneously. So if you look at this diagram, you have a wave going on forever. That will mean that you can exactly find out the wavelength of this case, okay? Because you have very long wave going on and all the wavelength, you can work out the average, you will find out exactly the wavelength. Once you know exactly the wavelength, then you don't know the position. Position is going around in a circle, it's a big one, okay? So the position graph you can see is having a width. Now similarly, if you have the momentum is broad, then you can work out the position, okay? So the next slide I can just skip, it's just the same idea. I don't have to go into because you don't need to work out the relation for momentum. This is not the idea to see. Okay, quantization. This is also the second part of the experiment which led to the Nobel Prize. Okay, quantization is that it's a very strange kind of bucket. This quantum state is like you have a bucket which is 15 liter. You have 15 liter of bucket, and this bucket you can add water of 15 liter, you can add water of 5 liter, but you cannot add water of 10 liter. It's very strange. It's a very big bucket. You can add water of 15, you can add water of 5, but you cannot add water 10 liter. In between, you cannot add anything. So it's a very strange thing. So inside here in a quantum system, it can have a discrete value of energy as well. So the energy of the system is always quantized. So it could be one value here and another value here. It could be 13.6 eV and then it could be 14.9 eV. In between, no, it's nothing. Okay. So this is a very powerful thing that led to the Nobel Prize, and it is used in the quantum computing. This is why the Nobel Prize was there. Okay. So perhaps you've heard, those of you who have gone through the quantum mechanics course, particle in a box. Particle in a box you can write down in terms of a peculiar equation, and that peculiar equation you can convert into just single D. the reason that I'm showing you is that if you look at this equation, in the denominator you see L squared. Okay, in the denominator you have L squared. I mean, if this L is very big, the L squared will be very big, and then 1 over L square will be very small. 1 over L square very small, it means the energy will be very small. Okay, so that means in order for a particle to be considered as a quantum object, it has to be bounded by a system. This is very important, bounded by a system. Bounded by system does not mean that electron should be just bound to a nucleus, then it will be considered. Otherwise, you can think of, for example, molecule as well. Okay, so it's not bounded by system doesn't mean bounded to the nucleus. Bounded by system means it should have a boundary around it. Okay, for example, a particle inside a wall. You have also studied the particle inside a wall in your quantum mechanics course. Okay, so this thing will give you, if you have a very big system, then you can afford to have a bigger particle as well. Right? This is the main idea which led to the Nobel Prize, quantum tunneling. Okay. Normally, perhaps you have seen it on the social media as well, video as well. They will show you a tennis ball hitting the wall, saying if you hit a wall with a tennis ball, the ball will be reflected back, will bounce back, it will not go through. Okay, but this is a very strange kind of ball. Quantum object is a very strange kind of ball. When it reaches a wall, it looks at the wall. Sometime it can happen, sometime it can happen that the ball will pass through the wall, depending on the height of the wall, depending on the width of the wall. That's important. Depending on the height of the wall, width of the wall, and also energy of the wall. I think sometime I'm losing this thing. Okay. This is a peculiar example shown in many of the books and social media as well. So you have somebody who is classical in nature. So the classical person would say, okay, I have this load, I have to take it to the other side of this mountain or this hill. He will start going up the hill, and then will take it to the top and then roll it to the other side. Okay, this is one way of taking it. But you need to spend a lot of energy. But here comes the quantum. Quantum says, no, you don't have to go up. I have the ability to pass through the mountain, provided the mountain is not big enough. So why does it do so? Because we say that quantum objects has two properties. It has a particle property and also has a wave property. So whenever a wave encounters any barrier, you should listen to this one. Whenever a wave encounters any barrier, it just goes down to zero exponentially. Exponentially does not mean vertically going down to zero. So inside this barrier, it will go down to zero, keeping the same fashion of the wave. It goes down to zero. That will mean towards the end, if it is passed through the width, if the width is not too much, then a part of this wave will leak through. Okay, and that leak through will then again be pushed away. What happens is that whenever this particle, this quantum object, is out of this potential well, then for example, we are going to give you example of the alpha particle as well. Out of the nucleus, you have the Coulomb force between. There is a Coulomb repulsion. The Coulomb repulsion tells you that the positive will repel each other. So if you have a positive quantum object going out of the nucleus, you spend some energy on it. The moment it is out of the nucleus, it sees the Coulomb force. The Coulomb force repel it, so it will gain further energy. This is just like when you have this alpha particle. You have a uranium nucleus, a very huge nucleus, 238. Inside the nucleus, you can have many alpha particles. But let's say one alpha particle, alpha particle is a helium nucleus, right? It has got 2 protons and 2 neutrons, it's a positively charged, okay? And it suddenly decides, okay, I'm going to go out. Okay? This is a quantum phenomena. Disintegration of the bigger nucleus into smaller one is a quantum phenomena. Okay? So this nucleus will disintegrate, so the alpha particle is going out. Now this alpha particle is having energy very small, very small, even 10 times smaller than the binding energy of the alpha particle inside the nucleus. Okay? So one would think that how come the alpha particle would leave? But the alpha particle leaves because of this quantum tunneling. So the alpha particle leaks through the wall. This is the potential will of the nucleus, and then outside it receives the Coulomb force, so it will be repulsion, and this repulsion leads to then the high energy alpha particle going out. Okay. This is quantum superposition. I'm sure you have seen this picture as well. It's again very strange. This is very confusing for quantum particle, that a person is dead and alive. Okay, a cat is dead and alive. Don't repeat this experiment at home, please. Yes, please. Yes, please.
My question is, do we know why and how the quantum tunneling happens?
Right, I'll share with you. The quantum tunneling is basically because of the dual nature of the quantum particle, the quantum object. Because when it is, as I said, when it reaches any obstruction, then the wave goes down to zero, but it doesn't go down to zero vertically. It goes down to zero exponentially, and the exponential goes inside the barrier, and inside the barrier, if the width is small enough, then it will go out. Okay, right? Okay, good. So now, this cat experiment was never done, by the way. It was not done by Schrödinger. It was just a thought experiment. Okay, so I urge you, do not try to repeat this at home. Okay, so the cat, what we are saying is the phenomena is quantum. So what you have this cat inside a box. The box is let's say covered with steel metal thing, and you have no access to approach or to see. Seeing is also very important. You don't see it. Okay, so now what happens is, inside you have a bottle full of poisonous gas. Okay, and then you have a radioactive element inside the box as well, and on top of that radioactive element you have a Geiger counter. The Geiger counter, the moment it sees a particle going into it, it will click, and the click is attached to another bar. When it clicks, the bar will shatter the bottle. When the bottle is shattered, the poisonous gas will be out, and the poor cat will die. Okay, but since it's quantum, it could be at two states, it's a superposition of states. It means it could be just giving radiation, it could not be giving radiation. We don't know. And it's in both states possible. So it's both states possible. It means until and unless you open that box and look into it, you don't know whether the cat is dead or cat is alive. But the only thing quantum says, don't say the cat is either dead or alive. Just think about this one. It's not saying either dead or alive. It says it is dead and alive. So this is a different, okay? It's not saying either dead or alive. It says and. It's dead and alive. So in quantum mechanics, the state, the superposition of state is not just 1 and 2. Okay? It's both. State 1, for example, a particle, until and unless you look at it, it can have spin up as well as spin down, until and unless you see it. Once you look at it, it can have spin up or spin down. So before measurement, the wave function will be intact, and then it will be in both. Okay, so this is the big difference. It's in two states simultaneously. Okay, there is an and in between. Okay, there's no or, it's and in between. Okay, now this is just simple mathematical things. Those of you who have not gone through perhaps will find it very boring, so I'm going to be quick with this one. It's up and down or 0 in one state, and you have the probability, and this thing you don't go, just don't bother about this one. Quantum state interference. This is another beautiful thing about quantum mechanics. This interference is a little different than whatever you have learned so far. The key characteristic is it relies on the probability, and adjust the amplitude, and then you make the square, then you have the square of the real part. Remember, when you have the amplitude of 1, you add the amplitude of the 2 instead of taking the square of the 2. So when you add the amplitude of 2, just like a plus b squared, a plus b squared is a squared plus b squared plus 2 times a and b. But here psi 1 and psi 2, they are both complex. So you have psi 1 and psi star, which is a complex number, meaning you have an iota in between, right? You know this, right? Complex number. So you take a square, then the square will be a plus iota b into a minus iota b. So you get a real part, and you also get the imaginary part. So what we are interested in is the real part. So the real part is giving you the interference term. But you will see that even in classical mechanics and waves mechanics, you study interference. You have crest and crest, they will interfere constructively. You will have crest and trough, it will interfere destructively. And if you have trough and trough, they will interfere constructively. So it was there, this term was there. So what is big deal in quantum mechanics? Why we are saying it's different? The quantum states are different. Now it's come the real part of this one. You'll see here. Okay, look at this picture. Double slit experiment, you have done it before, right? You have seen it before. So you have, when you have done it perhaps with lights. So when you have the lights going in and hitting these double slits, and you see the fringes at the back. Okay, this is the normal thing. But if you have a source, and then when both the detectors are off, there are two detectors. If there is any particle, a quantum object pass through one of these slits, if the detector is on, then it will be different. But if the detector is off, then you see this interference pattern. Look at the center spot. The center spot, the biggest one, the brightest one, is in line with the obstruction in between the two slits, right? It's just going along the line. In between you have obstruction. Normally you would expect a dark spot because it's the obstruction, in line with the obstruction, but you see a bright spot. But this is not the reason this is different. See, if you have single particle, this is where it comes the funny part. It's not many waves coming in, just one particle at a time, one electron is coming in. One electron is going to hit this double slit. Now you will see just one particle. Why would it just give you the interference pattern? Because it has not gone through two slits. You would expect, but you still get the interference pattern, provided those detectors are still off. The moment you switch on the detector, then you see this thing. Okay, so there are two big differences. Number one, there is a single electron system, single particle system, not like the waves you have studied before, not like the classical case. One electron is going through there and then is giving you the interference fringes. Okay, and number two, there is a detector. The moment the detector is on, it gives you the measurement. So the no path, in inverted comma, no path. When you know the path which it follows, then you don't see the interference fringes. That will mean the quantum nature disappears. What we call is decoherence. When it interacts with the environment. Whenever you start observing a quantum object, it is no longer a quantum. Okay? So the moment you will find it, of course it will be there, but then the quantum properties after that time will disappear. So here the thing is that this thing is giving you two things. Number one, that we are having a single particle. What does it tell then? If a single particle is giving you interference? Yes? Any taker? There's a single particle still giving you interference. There was one electron going in there and still you got interference. Why? Wave nature, brilliant. It's because of the wave nature, because there was a single electron going there, but it's got associated with it a wave nature as well. So the wave nature is just giving you the interference. And number two, whenever you have the detector on, that means the wave function collapsed. Okay? The no path is just collapsing the wave function, so it's no more a quantum, so you don't see the interference. Okay. This is another very beautiful thing. This was also, I think 2022, I'll share with you, was the subject of a Nobel Prize, 2022, quantum entanglement. It's very common in quantum computing. This is a very strange phenomenon. I have something with me just to demonstrate something. I wish I had I normally carry some envelope with me. I don't know, I have no other envelope. Can I borrow envelope from someone? Somebody has an envelope or something like this? Any bag? Do you have an envelope? Yeah, please. कभी मदारी को अटेंड किया है? मदारी हैदराबाद को उठा है. Thank you. I have two balls. Can somebody tell me the color of this one? Pink. Green. So pink and green. I'm going to put it into these envelopes, okay? So you don't know which one, but you know it. Okay, don't look at it. Okay, I have changed it. Okay, so they've gone into these two, okay, and these envelopes. So one is pink, another one is green. So you know that if you find out the one green, then you know the other person will having the pink one, okay? So better this is one is going towards you, whosoever catches it, okay, I'm better. So whosoever catches it, okay, good, okay, give it to him. Okay, you can throw it back as well, so it's far away. Okay, so don't open it yet, okay? So now, but if you opens it, okay, now instead of telling your color, tell me the color that person will have. Color of the ball that person have. Not your color, okay? Tell his color, okay?
Green.
You have a green? Now see if you have a green. He has a green. This is a picture to say what entanglement is, but the only thing is this is wrong, okay? The idea was not to say that this is it, this is wrong, okay? But this is yours now, keep it, okay? It's yours, better keep it, this ball. The thing is, with the quantum objects, you never know the color while going from here. This ball was always green when I put it into the box, into the envelope, okay? It was always green. And yours one was always pink. Okay, it's not that it changed in between. The quantum object is what I said at the beginning. Remember, I said it's not either, it is and. The ball you received was always green and pink. Okay, of course the classical one is different, but quantum, this was always green and pink, always pink and green. So the moment she saw that one is pink, that's how it changed into the green one. This is just like another example normally given is that of a pair of magic gloves. You know, gloves comes in pair. You have the left and right, okay? So if you have a magic glove pair, and then the magic in a sense that until and unless you put it in your hand, you don't know whether it's a left or right, okay? It's not like the one you get it in the store these days for doing the experiment in a lab where every pair is just the same. It's not like this. It's just left and right, but you don't know until and unless you wear it. So the moment somebody wears it and he says, okay, the other person is having if that person finds it right, the other person will be having the left one. But it's always in between, and this is the beauty of entanglement. So if you have a particle, for example, a photon, one single photon, you hit it on a polarizer. A laser is hitting, source is just one single photon coming out, you hit a polarizer, and there's a splitter. The job of a splitter is to split the beam into two, okay? So you have a splitter which is a polarizer splitter, and the polarizer splitter will have a horizontal polarized light going in this way, and the vertical, for example, going in this way. So you have the polarizer which is split the beam into the two different polarization. But you don't know until and unless you put another polarizer to find out what is the direction of that polarization. Okay? It is both. It is up and down, it's horizontal and vertical. You don't know. So similarly, you have another system which is just giving you one electron source, single electron source, and then could be a spin up and spin down. They are together. Okay? So some people, they give you the example, please don't go by that. They normally say, okay, there are two friends. Or somebody says conjoined twins. Conjoined twins will have the same habit. You ask one person another thing, the other person will give you the same answer. So it's not like this. So what happens here on quantum system or quantum object, you do experiment on one quantum object somewhere in space. If they were entangled, you don't do the experiment with the other one has done the experiment. If the wave function of one of these entangled particles is collapsed at somewhere a distant galaxy, let us say Andromeda, here on the Earth, this wave function will be collapsed for this object as well. Okay? So if this was, for example, spin up, this one is directly spin down without doing any experiment. So you would imagine the interaction is there, is simultaneous. It's simultaneous. It means it's not taking any time. It's not taking any time one would expect. This is just the violation of the famous Einstein relativity relation. Okay, special relativity. Where special relativity we says that no particle or no information can be processed with a speed greater than 3, not light, don't call it like this, this is exactly why I'm saying it, then 3 into 10 power 8 meter per second in vacuum. Do not use the word light with it. It so happens that light has this velocity in vacuum. But the actual thing is, this was the speed which was worked out. Okay, so communication or communication of information or matter cannot be sent in space. The space by itself can exceed the speed of light, by the way. The galaxies are receding from us with a speed greater than the speed of light. Okay, so the space by itself is stretching. Okay, the space and time is stretching with a speed greater than the speed of light. But nothing can communicate in space, in free space, with a speed greater than 3 into 10 power 8 meter per second. Not in vacuum. Vacuum speed is less. Okay. By the way, phase velocity is another concept, which is just the relation of omega with k, can be greater than the speed of light, but phase velocity is not like group velocity. Okay. So this entanglement is a very powerful tool. The Chinese are quite ahead in this tool. The Chinese have done experiment, and they have now demonstrated to quite a few kilometers that you can have two particles entangled together. So that could be used for communication as well. Just imagine, you have done experiment here, it could be done somewhere else as well. So the particle entangled. And this was one of the reasons Einstein was never happy with this concept. And famously, he has been quoted as saying, a spooky distance, spooky action at a distance. Okay, but this, I'm not sure, but this is what normally the literature says. Whether he said it or not, but this is ascribed to him. Okay, now let's enough for this one. These are the people, by the way, who got the Nobel Prize for it. You can see this 2022 Nobel Prize was awarded to these three people for doing the experimental entanglement. Just to relax you a little bit. It's not only to relax you, I should just select a point as well. So if you look at the, just a small sentence, what is going to help you is, although tiring, always it is tiring, whenever you try to go uphill, but it is certain that it will elevate you. You go from this place, up there, you will get tired, but the position over there is having a high altitude. You work hard, it will be tiring, but the hard work will take you up there. Okay, so never get dejected by hard work. Okay? Now let's come to, once again, it was all your Qurban.